Good evening. Thank you for joining us. Thank you for making the time to be with us today. We talked about Chomsky normal form last time. Anyone has any questions regarding that from the previous class? No, yes? Before we move on to a new topic. Yes, no, maybe. All right, cool. So it looks like there are no new questions. Right. We want now to move to chapter 14, I believe, which talks about PDAs, okay? So we want to find out how PDAs or push-down automata fit into this whole picture, right? So PDA stands for push-down automata. So it's push-down automata. Because we've dealt with finite automata, right? We now want to deal with a newer machine that accepts context-free languages. Right, so a push-down automata is the acceptor of context-free languages, and it has got the following properties. Right, so you're going to have number one, an alphabet of input letters, right? So whatever it is that we're using or that is describing the language. So we are using A, B, I think up until now. We've been using alphabet A, B. Number two, an input tape infinite in one direction. Initially, the string of input letters is placed on the tape, starting in cell I. So we need a tape, right? The tape will be the record of input. So we have a tape that has got cell addresses, I, or whatever numbering system there is, right? So this is the tape. The input resides on the tape. So we want to say input resides on tape. On tape. This is the spoon that feeds the machine, right? So everything comes through it. Number three, an alphabet of stack characters. So I'll come back and discuss this in a little while, right? But let's discuss this now. Number four, a push-down stack, infinite in one direction. Initially, the stack is empty, that is, it contains blanks. So what is a stack? So let's take a pause and then go to describe the stack. A stack is a last in, first out queue. It is a last in, first out queue. Now, how does it operate? Right? If I use this analogy to say, if you've seen the magazine of a gun, right? What it has inside, it will have a spring that is sitting underneath, right? Or a spring mechanism. It may not necessarily be a spring, but a spring mechanism. How it operates is that when you put one bullet in, it compresses the springs and locks. If you put another bullet, it further compresses the spring end and locks. So if the magazine is full, the spring will be at its lowest, right? So now, if you take one out, if you offload the chamber of the gun and the top one is collected, right? You see the spring increasing, right, to cater for that space, up until you see it increasing as the bullets go, right? But the reason I'm using this analogy is that once you do that, you realize that the bullet that you put in first will be residing at the bottom of the pile, right? And the bullet that you put in last will be sitting at the very top. So the last bullet that you put in is the first bullet that will go out. So that is our last in, first out scenario. Right? So that is the stack and how it operates in its behavior. Right? So we said the stack is initially empty; it is filled only with nulls, right? And then after we interact with it, we can find other elements in there. But how do we interact with it? We interact with it using an alphabet of stack characters. So this alphabet of stack characters is given by you. So you give, or given by by you. The alphabet of stack characters is given by you. Right, so now, number 5, we've got one start state. We have one start state and it has got only out edges and no in edges. Right. Number 6, we have got hold states. Right. We've got hold states of two kinds. You can either be accepted or you can be rejected. They are only in edges and no out edges. Once you have reached a reject or accept state, you cannot leave. Right. Then number 7, you see we've got a finitely many non-branching. So finitely means we can have as many as one. Non-branching means it has got only one output. Right? It has only one output. There's no restriction to the input. We can have 5 inputs, 3 inputs, whatever, but the only output that it is 1. So that is the only restriction that is there, or that is the implication of non-branching. Right. So we've got many non-branching push states that introduce characters onto the top of the stack. So whenever you see push X, you're saying there is your stack which is empty, maybe at this point in time. Empty, 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 right? If you see push X, what then happens is that you now have X and then you have empty, 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 empty. All right. So that becomes the impact of push X. So it interacts with the stack. Right. So you can see here, it also says where X is the letter in the stack. Right. So number 8, we've got finitely many branching states. So branching states means you can have multiple outputs. Multiple outputs. So that is what branching means. Right, we've got two kinds. Read state. Read, it collects information from the tape. Collects info from tape. Right, that's the job for read. So we say it has got out edges labeled within the letters of the input alphabet. And also you can have blank character on it. Right. Then you've got number 2, the second branching state. We've got a stack, or the one that operates on the stack. We call it a pop state. So pop state, it eliminates elements, topmost stack element. Topmost stack element. All right. Then next, so these are the 8 elements of the PDA. Now, let us look at how this changes things in our world. Right? Let's say we had finite automata. Where did it fail? Right? We remember when we dealt with, or if we did it together, when you dealt with finite automata, and we did the pumping lemma section, we said we proved that this language could not be accepted by a finite automata, right? But we also knew that A star, B clean star could be accepted by the finite automata, right? We have a regular expression for it. We can draw a finite automata for it. So you can have a B and go there, then you have got your B's, you can have your A and stay here as many times as you want. Then A, B, B, A, B. So this will be the finite automata for that. But words such as A, B, B could be accepted by this finite automata. You have A, B, B, right? It could be accepted. But you could not draw this finite automata to say, this is the finite automata for this language. Right, remember, our machines are wrong can be wrong in either one of these two ways. Number 1, it accepts another way that is not supposed to be in the language. right? It accepts a word that is not supposed to be in the language. Or number two, it rejects a word that is supposed to be in the language. So in this case, if we say this finite automata represents this language, we are saying that words such as A, A, B, 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 which are also accepted by this finite automata, are in this language, which becomes wrong. So we need an accurate representation, right? We need an accurate representation of the language under description. Right. So how does the stack, or what was the failure of this? The failure of the finite automata was that it could not keep count. Could not keep count. Right. It could not say, I have had 5 A's, so I now need 5 B's. It had no capacity of doing that. Right. So what's so special about the PDA? The PDA gives us, or the introduction of the stack into the PDA gives us the following ability. Right. Say, let's take this for example. Right. We've got 3 A's and 3 B's. How do we know that we have got 3 A's and 3 B's? We will never know that we have 3 A's and 3 B's, right? We won't have a machine that will say we have 3 A's and we've got 3 B's, right? We do have those machines now, but I'm saying in terms of PDAs, our machine, the output of our machine is not going to be 3 A's, 3 B's, no, or 4 A's, 4 B's, whatever the case is. It will not be that. The output of our machine is whether a word is accepted or is rejected. So we do not actually need to quantify how many A's and how many B's are there. But we need our machine to be able to recognize equality of sorts. So for the machine to be able to recognize equality, we do the following, right? So our stack allows us to push in. So with a push, we put elements in. And with a pop, we take elements out, right? So imagine this. If we were to put these 3 A's into the stack, right? So we say, if whenever you read an A, push it into the stack. So you read the first A, 1, 2, 3, 4. Initially, your stack is like this. Step 0. Then step 1, if you read an A, you push something into the stack, a representative of that A into the stack. So let's call it, you put a $sign into the stack, you read an A. So you now have 1, 2, 3, 4. So you've now, but there's a $sign now in the stack. You read another A, you put another $sign in the stack. So 2, you read another A, you put another $sign in the stack. So you've now $sign. You read the third A, you now have another $sign in the stack. Now $sign, okay? Then you are done with these A's. Right, now you want to confirm that the B's that follow are equivalent to the A's that we have gone through. Right. So now, if you want to make sure or to keep that equality, let's remember 2 things. Initially, our stack was empty, right? So if we were to empty this stack, right, using each B removes an element of the stack, each B removes an element of the stack, what you realize is at the end, after these 3 B's, our stack will be empty. Right. So let's go that. Let's do that. Number 4. 1, 2, 3, 4. If we read a B, so we're saying read B, pop, a $sign. Here we are saying read A, push that. So now, if we read B, we pop, we now have $sign. So now $sign. And then number 5, if you read another B, we now have now, then $sign. And then number 6, if we read the last B, we're going to have 1, 2, 3, 4. Now, and the last one is out. Right. So what you have seen is that if there is equality, right? If there is equality, if you're checking for equality using a stack, right? You push the first clamp that you're checking into the stack and you measure it against the second clamp. But if there is equality, the stack that is initially empty at the end of the word should be empty as well, right? So it should be empty as well. Initially, the stack was empty. At the end of the operation, the stack should be empty as well. If the stack is empty when you are done with the word, then we say that there is an equality that has been preserved. Right, any questions? Is it being understood? Is it understandable? Right. So there's a question that says, how do you check for empty stack? So to check for empty stack, when you start, if you were to pop the stack, right, and you find that the result is you are no longer popping out anything, we are popping out now, or an empty, you're popping out now, then the stack will be empty. You know the stack is now empty. Does that answer you? So, Anthony, right? Right. So that's that, right? So that is how we can check for some equality. Now let me present a situation, right? Let me present a situation. Let's say we've got the word A, B, B, right? There is no equality there. What will happen? What will happen? So we've got the A's, initially we have now. The next we have got now. We put our dollar sign once we read that. Then you read in A again. You read in A, you now have a dollar sign. Now. Then you read again. You read an A, you now have a dollar sign, now, right? And then after that, you start reading B's. So we said when you read B's, you now take out a dollar sign, right? So you read the B. You now have two dollar signs left. You read another B. You now have a dollar sign left, right? So you have read two B's, right? And you get to the end of the word. So the end of the word is also signified by now. At the end of the word, if you read now, we are saying when you read this now, when you get to the end of the word, the stack is not empty. Therefore, we can say that there is no equality in the. We can deduce that the word is not equal. Therefore, it does not belong to a language. To the language of A to the power of N, B to the power of N. Right. Now let's draw the PDA for the actual A to the power of N, B to the power of N, where N is greater than or equal to 0. So they said we start, then or outbound, then what is a computer? A computer is a machine that accepts input, processes, and produces output. So once we start, we just turned on the machine. We now need to get input. Where do we get input from the tape? How do we interact with the tape? We read from the tape. So you go and you read. Right? What are you expecting to read? You can either read an A, you can read a B, or you can read a now. So those are the elements of the input alphabet that are available. Right? So now it is possible. It is not possible to have words that start with a B, right? Because when A is 0, when N is 0, now is only that is accepted. So now goes to accept. But B, there's no way that B can be accepted under these circumstances. It goes to reject. Right, words can start with an A. Once we have an A, if you read an A, we said we want everything here to be pushed into the stack. So read an A, now processing is putting it into the stack. Right, and the output is going to be $*, a $sign in the stack. Now, non-branching push states only have one output branch. Right, we have now read, we have processed, and we have an output, right, of a $sign in the stack. We now need to collect the next input. We read again. If you continue reading A's, we want to push a $sign into the stack. What you will see is already we have created a loop. Right? Read A, push, read A, push. So all these A's under A to the power of n are now catered for. But after the A's, or at this point, if you have read an A, you could read a B, or you could read a now. Right? If you read A's, then you are supposed to have some sort of B's. If there is no B, then we reject. So you note B. If there is no B, which means you read now after the A's, we reject. Now, if it so happens to read a B, we now need these B's to verify this number of A's. So if you read a B, you have taken your input, you have read it, we need to pop the stack, right? And once we pop the stack, we can either pop a $sign or we can pop a now. So if we were to pop now here, what would be the implication? If you were to pop now at that stage where you have read a B, it means that there's nothing that is inside the stack. You haven't been putting anything inside the stack because all along we've been loading elements into the stack. So when you pop the $sign, you want to collect the next input, you read again. If you continue reading A's or B's, right, you should continue popping the $sign, right? Up until you get to the end of the word. The end of the word is signified by you reading now. If you read now, you want to confirm that the stack is empty. You pop now, and then you accept. Right, so going deeper here with a read, right, you could read a B, or you could read a now, or you could read an A. If you were to read an A at this stage after another B, then the language is accepted. All right. So popping here, we can also pop a. If you then pop a $sign here, you go to reject. Okay, so that is an example of a PDA. Any questions? So we read a $sign here. Let me make it clearer. If we get to the end of the word and we read it now, we cannot expect anything to still be in the stack. Right, so you mean to say this one, right? Anthony, are you talking about this, where the pointer is? The one that we reject. Okay, yes, we need to label that. So we can read a B, if we read an A after this B, yes. We go to reject. Now there's a silver lining here. There's a silver lining. We can make a general assumption that if you cannot find a path for it, it is rejected. So if no path exists, then language is rejected. What does it mean? The only elements that we can simplify this PDA to remove all these reject states and only remain with accept states. Right, so we have something like this, and you can use for comparison. If we start, right. So let's start. Go to read now, then you go to accept. Then you read in A. Push in X into the stack, read, continue reading A's, read the B, pop, pop in X, read, continue reading at B's, you pop X, up until you read now, then you pop now, then you go to accept. Right, so these two finite automata are exactly the same, only that we have removed the reject states from the bottom one. Right. So it seems as if you understand. Cool. Now let's look at another question. All right. Cool. So there's a so Anton, I have a request, right? Is it possible to say when you send in your questions, just choose the option, say all panelists and all attendees, so that whenever a question comes through, the rest of the audience can also have visibility of it. So there's a question that says, so what happens when we read the wrong stuff? Let's read A, B, B. Start, read an A, right? We have got an X into the stack. We read another A, we've got a second X into the stack. Read another A, we've got a third X into the stack. Then read a B, right? You now move from here to there. You want to pop the stack, so this goes out. Right? So that's the first B that we've read. If you read the second B, then we take out this X. We're now left with one X. And then, because it says read a B, pop an X. And then we read. So we can either read A's or we can read B's, or we can read now. So if you read another B, and if you read another B, which is not there, so there's no other B. So at this point, after these two B's, you read, where's my pointer? You read a now, right? So once you read a now, right, you're going to pop, when you pop, you're going to find out in X is still there, right? So this is not a word in our language. So because we do not have a transition for read now, pop and X, right? It means that it is automatically going to reject. Right. So does that answer your question? Mm-hmm. Oh. All right. So there's another question here. Let me see. Okay. So that answers that. Now let's look at varieties or how this can differ. So what we can have is, for example, it's not always going to be equality, right? It's not always going to be equality. So we can have a b to the power of, or a to the power of n plus 2, b to the power of n, a to the power of n, b to the power of n plus 2. How do we deal with such? And so there is two ways that we can deal with this. We can either draw a machine that accepts this way directly, or firstly we can make sure that the machine accepts our given format. So the first method would be to say a to the power of n plus 2. If we done laws of our indices correctly, it will be a to the power of 2, a to the power of n, b to the power of n. Right, so next it would mean that we've got this bunch of a to the power of n, b to the power of n. What do we do? These a's are not affecting the stack. So when we start, we say read a, read a. So these two read a's do not affect the stack. Right. So the second way would be to build a machine generally for that. But I would like for us to deal with so for today, I want for us to deal with one method. Then tomorrow, I'm just gonna do multiple methods going together, right? So this simplification, what it does, or if we simplify this, we've got a to the power of n, b to the power of n, b to the power of 2. Right. So we can manage it like that to say it could be even be a to the power of n, b to the power of 2, b to the power of n. Right. So this b to the power of 2, after reading this a's, these two b's, it will be read b, read b, and you don't interact with anything. Right. So let's look at a question. A to the power of n plus 2, b to the power of n minus 2, a to the power of a. So using our method, we can equate this. So we're going to have AA we've got AA for this plus 2a's, then we've got a to the power of n, then we've got, but we need n minus 2 for it to match this one. So we need to take two more. So we've got a to the power 4, a to the power of n, right? So it's a to the power of 4, a to the power of n minus n minus 2 plus 4 will give us n minus 2, right? So we've got this, and we've got b to the power of n minus 2, and we've got a. So this one we simply read, does not interact with the stack. Right, so this one you push into the stack, and this one is the one you use to pop the stack. Right. So if we wanted to draw this, we would have read what can you read here? You read in A, and after that you're going to read again. If you continue reading A's, then if you read in A, if you then sorry, so we need to adjust something here. Things are going very fast here. So we said a to the power a to the power 4, a to the power of n, b to the power of n minus 2, n minus 2, a. So we said start, and then we go to read, and then we go to push y into the stack. But this is not yet necessary to say put y into the stack. We need to first get there. To get this 4a's gone. So you can only read one at a time. So you read in A, read in A, read, read in A, 1, 2, 3, we need one more, read in A. Alright, so when I have 1, 2, 3, 4, we've catered for this A to the power 4. Now we start on this one, A to the power of n minus 2. So we're going to read again. So we need to read. Once we read, we find that we need to push this a to the power of n into stack. So we've got a, read, a, if you read in A, 1, 2, 3, 4. If you read in A, 2, 3, 4. Okay, so it's supposed to be here. Right. So if we read, just give me a second, I'll be with you. 1, 2, 3, 4 have been read, so this is catered for. A to the power of n minus 2, we have read this A, we have read that A, then we push into a stack. Then we read again. So if you now read A, B, the instruction is to say, if you continue reading A's again. So if you read an A and you read another A, then continue to push. Otherwise, if you read a B, you pop the stack. You pop the stack and you find in what did you put into the stack, and X into the stack. And then you read if you continue reading B's, you pop the stack. If you continue reading B's, you pop the stack. Right, so let's come to a question. Right. So let me come back to, so the question is regarding how do I get to this one. So I'll come back to, just give me 2 minutes, I'll come back to that one now. So you read a B, pop a Y, read a B, pop a Y. Then after the B's are done, right, you can now start reading A. So you can read this A. That A does not affect the stack, right? Read an A, you want to read again, and you read another A. After that, you read A, and now, and your stack should be empty at the end of the way to pop A, and now then you accept. So I'll come back to this slide later, right? I want to address the issue of laws of indices. If you've got A to the power of 2 multiplied by A to the power of 3, do you agree that the result is A to the power of 2 plus 3? That's you, Chanel. Do you agree that it is A to the power of 2 plus 3? Right, if it is A to the power of 2 plus 3, if we've got A to the power of n plus 2, do you agree that this is A to the power of n multiplied by A to the power of 2? Right? If we agree that this is equivalent to that, okay, then we are saying if I've got A to the power of n, right, n plus 2, if it is equivalent to say A to the power of n minus 2 multiplied by n to the power of 2 multiplied by, so A to the power of 2 multiplied by A to the power of 2, right? So effectively what I'm saying, this is equivalent to A to the power of n minus 2 plus 2 plus 2. So minus 2 plus 2 becomes 0, plus 2 becomes A to the power of n plus 2. Right, so it's playing around with the laws of indices. So why did I move it from to the n plus 2 to n minus 2? Right, if I have n minus 2, I now have equality between what I'm trying to check. So this is now equal to that one over there. So, and I know how to check for equality inside my language. So then it becomes easier for me to check for equality with my machine. Right. So you can take this, right? Try words that are in the language. So we have got A, if n is equal to 1, we've got AA. If n is greater than 1, so n starts at 2. So we have 4 of these, so we have 1, 2, 3, 4, okay. Then we have got B to the power of n minus 2. at this point, if you've got 4 of these, a to the power of 1, 2, 3, 4, and then so we're going to have 6 A's. So I'm going to say 1, 2, 3, 4, right? Okay, so I see where I went a little bit wrong. So when I was doing this, I said it was supposed to be AA to the power of 4 and AA to the power of n minus 2. So I was supposed to have these double A's, there's double A's. I was supposed to have these as double A's. So there's a mistake in this machine that I've drawn. Let me correct it. So we're dealing with AA to the power of 4, AA to the power of n minus 2, B to the power of n minus 2, AA. So we're saying we start, you want to read an A, you want to read another A, you want to read another A, you want to read another A. So we now have 1, 2, 3, 4. We're supposed to initially start with 8 A's, right? So we've got 4, read 5, read 6, read 7, and read 8. So you might have a question, why not create a loop for this? Why not create a loop for this? We cannot create a loop for something that is a specific number. Once we create a loop, we are saying we can do this even for infinite. So it becomes wrong. So here we've got 1, 2, 3, 4, 5, 6, 7, and 8. So after these 8 A's, if I then read another double A, that's when I push it into the stack. Read again a double A, then I push X into the stack, and then I go and I read again. If I continue reading double A's, so how do I record double A? I read one A, then I go to another read state that read another A, then you push. Else I read a B. If I read a B, I pop. Right? If I pop, what am I getting? I'm popping an X. Then I go, I read again. If I continue reading B's, I continue popping this stack. Then I'm going to read an A. The A does not impact the stack. Read again. If you read another A, it does not impact the stack. Read. Then you get to the end of the word. If there is equality, we said if you get to the end of the word, right, the stack should also be, the stack, when you pop, the stack should be empty. Then you go to accept. Right. So when n is equals to 2, we said we've got 6 A's. So we've got 6 sets of A's. So we've got 1, 2, 3, 4. Right? We read the 5th one, we push. We read the 6th one, we push. And then at this point, we're saying, so this is the initial condition at n is equals to 2. After, when n is equals to 2, we may not read a B. If we do not read a B at this point, what do we have in the stack? What do we have in the stack? If you read a now at this point, because it's allowed to read a now at this point, if you read a now, you still have 2 elements that are in the stack. You want to empty it. You read a now, you pop the stack. You have the first X. You read a now. You pop the stack. Sorry, you now have another X. At this point, your stack is now empty. So you read again. And now, and you pop a now, and I'll explain the significance of this. You pop a now, then you go to accept. So this will be the machine. It's quite a big one. So for n is equals to 2, that is the initial condition. So that is the initial condition. You see, that is the only word that will be different from the rest. The rest would have B's in between, but itself does not have a B in between. That's why you have to cater for it. So number one, always cater for the initial condition. Number two, right, why is it important for me to only go to accept after I've read a now and I've popped a now? So it is important for me to do that because that acts as a checksum. Your ID number has got a checksum. Your IMEI number for your phone has got a checksum, right? We need that checksum to verify whatever it is that the word belongs to the language. The absence of this, I could have said read now and then go to accept. If I say it at this point, if you read now, go to accept, what would happen is if I have, so I said read is, read now, then go to accept. I could read words such as a, which is not in the language, right? So when n is equal to 12, only 6 A's, right? If now I have 8 A's, right? I could still have the 8 A's because I've got a loop that is saying each time push an X, push an X, push an X, push an X, right? If I have that, it becomes, so let me say, I can even have up to 12 A's. If I do that, what then happens means, as long as I'm reading double A's, I'm pushing an X. And when I get to the end of the word, I do not verify how many X's that I have. So now, in this case, when n is equals to 0, n is equals to 0 says we're going to have 4 sets, these 8, right? And one set of, it's one set actually, it's one set of double A's, right? And that we put, so we push only one X, so there'll be one X inside. So I elongated this unnecessarily. So there'll be only one X that will be sitting inside the stack because of this one double A that is there. Now this one double A, I've taken it out, the X that was representing the double A. When I read again, the word will still be finished, but the stack will now be empty. Then I can go to accept. So this confirms that there was only one remaining X in the stack. It serves as a confirmation. Right? So you only go to accept when you have read a now and you have popped a now, so you've confirmed that the tab is empty and the stack is empty at the same time, then you go to accept. Right. So we're running a little bit short on time, so I'm going to have to close off this lesson. So what I've done is I've dedicated our Tuesday session, next week Wednesday. We're going to do a marathon of PDAs, right? So we're going to do a lot of them so that you can familiarize yourself and see how different questions can be asked and be comfortable with most of the scenarios given. All right. Okay, cool. Thank you very much for attending. Enjoy the rest of your evening. Good night.